Hi class. The next factor that we're going to look at that controls temperature is ocean currents. Okay. To do that, we're going to draw kind of a number line. It's going to be a latitude line here. And so we'll start off with the equator here at 0 degrees latitude and North Pole and the South Pole. Okay, and why I drew this is we're gonna take a look at the difference between incoming solar radiation and outgoing terrestrial radiation. Okay, so at the equator, we have lots more incoming solar radiation. So incoming solar radiation is greater than outgoing terrestrial radiation. Okay, so if you remember incoming solar radiation, whatever gets absorbed warms the planet, and then one of the ways that the planet cools itself is by emitting terrestrial or infrared radiation. Okay, so near the equator, the incoming solar radiation is always greater than the outgoing terrestrial radiation. Okay, and so as a result, we build up a surplus of heat energy in the tropics. Okay. And if we look at the poles, we have incoming solar radiation. Okay, so make it at both poles here. We have incoming solar radiation, but there's actually more outgoing terrestrial radiation. So the outgoing terrestrial radiation is greater than the incoming solar radiation. So there's more energy leaving the planet at the poles than there is being absorbed at those latitudes. And so as a result, we build up a deficit of heat energy at the poles. So really, if we look at this on a daily basis, okay, so every day at the equator or at the tropics, there's more incoming solar radiation than outgoing terrestrial radiation. So the next day, more incoming solar than outgoing terrestrial. The next day, more incoming than outgoing. And so this goes on day after day after day after day, okay? But are the tropics continually getting warmer? No, they're not. They're not continually getting warmer, even though every day you've got more incoming solar radiation than outgoing terrestrial radiation. Conversely, looking at the poles, okay, every single day you've got more energy leaving the polar latitudes than energy coming into the polar latitudes. Every day, day after day after day after day. And yet the poles are cold, there's no doubt about that, but are they continually getting colder? And the answer is no, they're not they're cold, but they're not continually getting colder. And the tropics, they're hot, yes, they're definitely hot, but they're not continually getting hotter. And so there's got to be a reason for that, and that is because the surplus energy is being transferred to areas where there's deficit. Okay, so we got a temperature gradient. Whenever a temperature gradient is established, heat energy is going to be transferred. Okay, in this particular case, since we're talking about ocean currents, you can be certain that ocean currents are moving some of this heat energy. Okay, I'm going to draw this up here, and actually I'm going to draw first atmospheric currents. So some of that surplus heat energy at the tropics is going to be transferred via atmospheric currents. And in fact, the vast majority of this surplus heat energy is being transferred by atmospheric currents. You can think of that as the jet stream. You know, if you want to just If you're more familiar with the term jet stream than atmospheric currents, go ahead and use that. But about 75% of this surplus heat energy being generated at the equator is being transferred towards the poles, okay, by the jet stream, by atmospheric currents. Okay. Now, again, we're talking about ocean currents here. So there is, down here at the surface, ocean currents. Ocean currents are also transferring some surplus heat energy, okay, much less than atmospheric currents are, but not insignificant. About 25% of the surplus heat energy being generated at the tropics is transported to the poles via ocean currents. So again, ocean currents don't transfer nearly as much heat energy as atmospheric currents, but it's not an insignificant total. 25% of the surplus heat energy is being transferred from the tropics towards the poles by ocean currents. Okay, so let's take a look at this figure. So this figure is one of the PowerPoint slides, so you can probably get a better feel for it. But if we look at the oceans, if you look at the west coasts of every continent and the east coast of every continent, it's really kind of interesting. On the east coast of every continent, the flow is such that ocean currents are coming from the tropics or the equator and heading towards the poles. And so on the east coast of every continent, let's see, here we go, the Kuroshio comma. So on the east coast of every continent, there is heat energy being taken from the tropics towards the poles by an ocean current. On the west coast of every continent, okay, so we've got the California current, we've got the Peruvian current, let's see, here we go, the Benguela current, the Canary currents. Okay, on the west coast of every continent, you've got cold ocean currents, okay, bringing water from the poles back towards the equator. So on the east coast of every continent, you've got warm currents. On the west coast of every continent, you've got warm currents. So if you look at something in the United States you'd be more familiar with. So right here, about 38 degrees latitude perhaps, San Francisco and Atlantic City, New Jersey. Okay, they're at nearly the same latitude. If you take a look at their temperature and well, take a look at the water temperature along the coast here, the California current temperature is going to be about 50 to 55 degrees Fahrenheit. You go over on the east coast at the same latitude, and the water temperature is going to be about 60 to 65, maybe 70 degrees Fahrenheit. So a 10 to 15 degree temperature difference of the water, of the currents, based on which direction that current is flowing. So on the east coast of the currents are bringing in much warmer water. The west coast of continents, it's much colder current coming from the poles back towards the equator. And as a result, locations on the west coast of continents tend to be cooler than the temperatures at similar latitudes on the east coast of continents. If you've ever seen the movie The Hunt for Red October, and if you haven't seen it, I highly recommend it. It's all about a Russian submarine, okay, that's trying to defect to the United States. Well, that Russian submarine was built, I think it's up in Murmansk, about 70 degrees north latitude, way up here. I'll put it, it's somewhere up here. And this is a major naval port for the Russian Navy. And it's like at 70 degrees north latitude, you would think, how do they have a major Russian port at 70 degrees north latitude. Isn't it mostly covered with ice year-round? And the answer is no. It's actually this courtesy of this ocean current. Starts off as the Gulf Stream along the eastern coast of the United States, and it flows up into, I think it's the Baltic Sea, and it keeps the Baltic Sea relatively ice-free. Yes, there are icebergs here. I'm not going to say there's no ice at all, but it keeps the Baltic Sea relatively ice-free to the point where the Russian Navy can have a major naval port at 70 degrees north latitude. Okay, so that's the effect of ocean currents on temperature. Next, we're going to take a look at the effect of altitude or elevation on temperature.